Yeah, thanks a lot for coming to this tutorial. Sorry for the delay. So the HDMI was not working, and it started working again once we turned it on and off. So yeah, sorry for the delay. All right, so this tutorial is titled an accelerated introduction to AI model deployment with cloud native. So before I get started, I hope you all had a great 2 days at the conference. So one of the things that I like the most about such conferences is that you get to meet wonderful people from the community who are doing great work in the open source communities. So one such person I met at the previous KubeCon is Emily. Emily was supposed to be my co-speaker. She is my co-speaker, but she was not able to make it in person to the conference, unfortunately. So what we'll do today is this tutorial has two parts. The first part is the machine learning side of things, and then I'll talk about how you can do that with Kubernetes. So what we'll do today is we have made a pre-recorded video of Emily's part of the talk, and we'll be playing it. And yeah, you folks can go through whatever we are doing. If you have a laptop, you can follow along, and I'll try my best to help you folks if you get stuck somewhere. So this is my first time doing one of these workshops. So fair disclaimer, I'll try to cover everything, and we'll try to do everything together. So this is a quick agenda for today. So first we'll look at what we'll be doing with scikit-learn and the array API. And for this part of the talk, we have a Google Colab notebook which we'll share with you, and you folks can follow along the video and then try running the code on your own. So for this, you don't need to install anything. We just need to have internet access. And once we are done with that, we'll go into the cloud native part of the talk. For this, we need a couple of things to be installed on your laptop. So if you don't already have it installed, I can help you with the resources with which you can do that. So we would need Docker. So you need to install Docker on your machine. And we also would need something called kind. Kind stands for Kubernetes in Docker. And we'll be using that to run a Kubernetes cluster on your laptop, on which we'll be doing things. All right, so first we'll look at the machine learning part of the talk, and then we'll go into the how you can do this with Kubernetes. We'll there will be a quick introduction of Kubernetes itself. So this tutorial is part of the cloud native novice track. So if you're someone who is already an expert in Kubernetes, some of this might be repetitive to you. But yeah, we'll take a look at Kubernetes, how you can Dockerize your machine learning applications and run them on Kubernetes. And yeah, with that, we can get started. So these are some of the resources that we want you to have. So you will have access to a Google Colab notebook where we have all the array API code that we'll be using, and that will be going through in the talk. We also have a GitHub repo where we have, again, all of the code and some other information with which you can run this code. And you also get a link to the slide deck where you can find Emily's video, and you can refer to that also if you're interested. I'll give you all a couple of minutes to scan the QR code before we get started. So for a quick survey, can everyone who has a laptop with them please raise their hands? I just want to get a quick idea of how many people will be following along. All right, thank you. I hope you all have scanned the QR code. If at any point of time, if you would need anything, if you need any help, you can let me know. You can raise your hand and let me know, and I'll help you out. All right, I'll start with the rest of the talk now. So yeah, again, these are the requirements that you would need to have. For the first part of the talk, you don't need to install anything. You can do everything online. And for the second part of the talk, you would need to have Docker, Kind, and kubectl installed on your machine. So if you don't already have those installed, I can help you install these. Yeah, please do let me know. So a quick introduction about myself. My name is Sreeram Venkitesh. I have been part of the Kubernetes community for about 2 years now. Yeah, I've mostly been active in the SIG release community of Kubernetes, where we coordinate releasing Kubernetes every 3 months. Now, for Emily's part of the talk, I will play a pre-recorded video where she will walk us through the entire scikit-learn array API talk that she's giving.
Hi, everyone. Thank you, Sreeram, for the introduction. Thank you for coming to our talk. Let's get started. Hi, everyone. My name is Emily. I am an open source contributor to the scikit-learn library, and I was also an intern at Probable, which is scikit-learn's official operating brand. I'll begin with an introduction of what is the scikit-learn library and what is the Array API standard and how those two things work together. So scikit-learn is an open source Python library for machine learning that focuses mainly in data science and is used widely in academia for data mining, analysis, and predictive modeling. Scikit-learn focuses on shallow networks versus deep networks like language processing. Therefore, scikit-learn is good at classical machine learning algorithms such as classification, regression, and clustering. That was a very brief overview of the scikit-learn library, and now let's dive a little bit into what is Array API. Array API is a specification that standardizes the core functions and behaviors of array libraries in Python to improve interoperability. What that really long sentence means is that because Python is entirely open source, there exist a lot of libraries that Python programmers can leverage so that they can use functions out of the box versus writing them from scratch. This is really convenient, but there is a slight problem with that. There are a lot of common functions in more than one library. You could do sum and main from a lot of libraries that exist for Python, but their behaviors are slightly different, as in they expect different inputs and different outputs. The input could be different numbers of inputs, different types of inputs, and different formats. This makes working with these libraries a little bit difficult because you can't use more than just one library in the same project unless you do some modification in between them to make them interoperable. The Array API standard aims to address that problem by standardizing common functions like sum or mean so that they work the same way across different libraries. So that means sum and mean and a lot of other functions are expected to have the same type of input, same number of inputs, and same type of output, same format of the output, as well as the same number of outputs. In scikit-learn, though, there are three main things that we are trying to achieve by adopting Array API. Most functions in scikit-learn are written in NumPy, which is CPU native, and you don't see a problem when your dataset is small. But as your dataset increases in size, you'll notice that CPU training becomes quite slow. With Array API, these CPU native algorithms can run on GPUs because we're able to feed them a GPU namespace array such as PyTorch or QPy, and therefore the training can happen on GPUs and it will vastly increase performance. There is something called just-in-time compilers or JIT compilers, which compile code while the program is running as opposed to compiling everything before runtime, then it runs. As you can imagine, this greatly increases performance. However, JIT compilers have very strict expectations on the input, output, and behaviors of functions, which currently aren't aligned with what scikit-learn has to offer. However, Array API standards expectation of these functions are exactly the same as JIT compilers, which means that by adopting the Array API standard, we will be able to leverage JIT compilers as well. Similar to JIT compilers, Dask arrays also have very strict expectations on the behavior, input, and outputs of functions that you would like to use Dask arrays on, and Dask arrays expectations also align with the Array API standard. In the current stage of the Array API standard adoption in scikit-learn, we are mainly focused on getting the first point across, which is getting NumPy functions to not only take NumPy arrays, but rather get all of our functions running on GPU first so that performance can be increased. Without further ado, let's get into the demo that I'll be running on Google Colab. I believe Sreeram has already shared this file with you, but if not, feel free to interrupt, pause the video so that you can type in the commands that are shown on the screen and follow along on your own laptops.
Does anyone not have the link to the Google Colab? If yes, I can show you the QR code again. Yeah, just give me a second. Okay, the video file, I'll update the access later on, but but you do have access to Google Colab, right? You might have to copy the Colab document because you might not be able to run it. So if you open this link, this is the notebook that is shared with you folks. If you're not able to run it directly, you might have to go here and make a copy of this. You can click on Save a Copy in Drive and you'll have a copy of this notebook in your Google Drive. So if there is anyone who is still not here, I can show you the link again, else I'll go ahead with playing the rest of the video. Yes, the PPT link is already there. The third QR code gets you the PPT. There are links to all resources, the PowerPoint presentation, the Google Colab notebook, as well as our GitHub repo. It was mentioned that the video in the presentation, like folks don't have access to play the video. I'll change that after the talk. All right, I'll start the rest of the talk.
Without further ado, let's get into the demo that I'll be running on Google Colab. I believe Sreeram has already shared this file with you, but if not, feel free to interrupt, pause the video so that you can type in the commands that are shown on the screen and follow along on your own laptops. Before I actually get to the demo tutorial though, I need to acknowledge that the code I'm about to show you is adopted from Olivier Grizel's code. Olivier is my mentor while I worked at Probable, still is my mentor as I'm still the contributor to scikit-learn, and he is a core dev on the scikit-learn team. All right, so this is the code I'm running through the demo. For the interest of time, I've already started running some of these, but just know that if it just keeps circling, it's just because a lot of things are getting installed. Be sure, first of all, that you're connected to a T4 GPU runtime because you will be needing this in later steps of the demo to use the GPU. This command just ensures that, yes, you are on a GPU runtime and that is connected and configured correctly. You should see this output. In here, you're cloning into my branch of scikit-learn, which right now is an unstable dev branch because I'm a developer on it, but this branch is this version is getting released very soon. Therefore, I wouldn't worry about not having these functionalities yet because they're due to release. This step is the equivalent of installing scikit-learn on your machine, but you can't really install scikit-learn the same way on the Colab, so that's what we're doing here. These two steps are just more things you need to install to enable the full functionalities and debugging powers of scikit-learn in this runtime. And don't be surprised if this takes a while to run, because as you can tell here, this has 251 things to install. All right, so after some time, our 251 things finally got installed, and you can see.
Yeah, sorry folks. If you are running these commands right now, I can wait until they are finished, or else what I'll do is I'll let the rest of the video play, and if at any point of time, if you have any questions, you can raise your hands and I'll come and help you out, and I can post the video there. Are we good? Okay.
See, we also have the dev version of scikit-learn installed in our runtime as well. This line confirms that we do have CuPy-CUDA installed. CuPy-CUDA is what we'll be using for GPU running later. This line installs Array API Compat, which is a library that already has functions written in Array API compatible format. This line shows that we indeed have scikit-learn installed. This line is quite important, so make sure you actually write this line. So SciPy is another library that is working towards Array API adoption right now, and SciPy is one of scikit-learn's dependencies. The requirement for SciPy to be Array API compatible is to have version 1.14.0 or above, so I am installing 1.14.1 here. This error is a very classic error that you see in this sort of Colab runtime. What you do is you hit runtime and then you restart session and run all, and that usually solves the problem. All right, so it's now running. I just cut out the waiting time between clicking restart runtime and now to save time on the video. But essentially all I did was what I showed you. So I clicked runtime and restart session and run all. Here are some of the imports that we'll be using in the later part of this code, and I'll explain it when we get there. Right now, Array API, so the GPU acceleration thing, is a choice in all the libraries that are trying to be Array API compatible. What that means is you can choose to use Array API or not. But if you want to use Array API, you need to tell the library that you want to use Array API. In SciPy's case, it's this line. And in scikit-learn's case, is this line. But what I foresee in the future is that once all the libraries, like the entire library, is Array API compatible, you no longer need to do this. But as of right now, these lines are required to use Array API functions, which means the GPU acceleration that I'll be using later. This line, I just assigned two very big numbers to n samples and n features. So I'm assigning 250,000 to n samples and 1,000 to n features. That means Later, I'll be using these two numbers to generate my data because I don't actually have data sets that big, so I'm just generating random data right now. This line means the mathematical function that I would like to fit across my entire data set for the prediction later. This section is where I will be generating the data. This is my data. So I'm using torch.rand to generate 250,000 samples with 1,000 sample each for every one of those 250 samples. I am storing that data in a matrix called W, and I'm generating the target or the outputs, the result of the data set using a matrix multiplication and some random noise. So essentially, data, target. Recall that CUDA is GPU, so I am converting the CUDA from GPU into a NumPy array so that I can feed it into the CPU or NumPy version. A perf counter is what I think of as a timestamp. So tick is the timestamp before I perform a function, and talk is the timestamp that I have after I perform a function. So once I subtract these two values, the time difference in between is how long that function took. In this case, I am keeping track of a fit and a print statement. Here, I'm feeding in the CUDA arrays of the ridge function. Array API will read that it is a CUDA array that is being passed into this ridge.fit function, and it will recognize that CUDA is compatible with GPU, therefore it will run the fit function onto the GPU. Similar story here. This line is identical to this line, except that I'm feeding in NumPy arrays in this case. NumPy array will be read by scikit-learn and recognize that it is CPU native, therefore it will run the ridge.fit function on the CPU. And because I also have a timestamp over here and over here that's wrapping around that CPU fit, we'll see how long the CPU fit took here. So the output of that block of code is this. I've generated 250,000 samples, each with 1,000 features, which works out to be 1 whole gigabyte of data. When I do the fit on the GPU, it took me 2.42 seconds. And when I did the fit on the CPU, it took me more than 1 minute. So as you can see, CPU is a lot slower than GPU, and you are able to do GPU acceleration on the scikit-learn library with Array API enabled. Some of you might be asking what these two lines are. Some of you might be asking what this line and this line mean. So these two lines correspond to this print statement over here. So essentially, I'm printing out the first 5 elements out of this rich CUDA.coif array. This array has 1,000 elements, which correspond to the number of features each sample has. And what these numbers mean in here is that what are the best weights of each of these features in the sample that give you the best result in terms of prediction. So what did we learn from this demo? 1, GPU is a lot faster than CPU when you're doing a fit function for machine learning. And 2, you're able to do GPU and CPU fits on scikit-learn with Array API enabled. So I have reached the end of my demo. I hope you all learned something from it. But before I go back to my slides, let me show you something that we're working towards in scikit-learn. So this is a meta issue that we have in the scikit-learn repo, and we're working towards completing that. So, and here lists all the functions that we're working towards array API compatibility so that you can use GPU acceleration in all of them. It's a very, very long list, and we welcome contributors to help out with this issue. So that is the end of my portion of the talk. If you are interested in chatting more about Array API or contacting me or contributing to that really long meta issue that I just showed, please feel free to get in contact with me. That is my Gmail over here, that is my LinkedIn, and that is my Twitter or X. If you don't catch it right now, I think Sreeram will show it at the end of the talk as well, so you will get my contact information either way. Before I end this video, I have 2 links for you over here. This one is more information on the Array API standard. That is the link to their official page that we're following. And this is the scikit-learn's official page. If you're interested in playing around more with this tool, becoming a contributor yourself, or just to learn more. So that is the end of my portion of the talk. I hope you enjoyed it and learned something from it. Now I will pass it on to Sreeram to do a similar thing, but on clusters and on Kubernetes.
All right. Thanks, Emily. I'll skip over all the slides. All right. So for the next part of the talk, we will look at how Kubernetes works and how we can do everything that Emily just showed on a Kubernetes cluster. So for folks who are new to this, I'll briefly give a quick introduction of what Kubernetes is and how all of these come together in the cloud native space. So containers containers is a concept that has been there in Linux for a very long time. C groups, namespaces, and all of that. But containers, as we know it today, was popularized by Docker in 2013. Docker changed the way we package and ship software. They made it easy. They made it easy so that you can run code on your machine as how you would run it on any other machine. So you wouldn't have the challenges of setting up a traditional virtual machine where you would have a different setup for your development environment versus production. So this diagram that we see here is a quick like a comparison of how containers are different from like regular VMs. So if you are using containerization technology to run your software, the underlying machine or the host in which the software is running would have a container runtime running. And this container runtime can be Docker or Containerd or CRI-O or any of these alternatives that we have today. And we would create container images which would have all the necessary information on what all we need to have to run our software. So if it was like if you were running this on a regular virtual machine or like a physical server on a rack, you would have to like install all the dependencies of your software to be able to run the code. And let's say if you want to replicate this across multiple machines, you would have to do the same setup across all these machines. So the difficulty here is that if you are trying to run the same code on different kinds of machines, different kind as in there can be different architectures, there can be different operating systems. And if you want to run your code across all these different kinds of machines, you would have to like do the initial setup in a different way. So you would have to like there would be one way in which you would be installing a particular dependency on a Linux machine versus a BSD machine or a Windows machine. And it would also depend on the version of the operating system that you're using. So Docker makes it easy. If you're able to install Docker on a particular host, be it any kind of host, if Docker is running, if the Docker container runtime is running, you would be able to run the software with the same Docker file across different different architectures and different kinds of machines. So that kind of technology was popularized by Docker in 2013, and it changed the way people think about shipping and packaging software. So what happened after that was we started seeing a very high adoption of containers because it made development lifecycle easier and faster, and it also let users run their code in their machines the same way they would run it on production. So we started seeing a very high spike in the usage of containers, and there came a need where we had to manage hundreds or thousands of containers. So it was at this point in time that Kubernetes was open sourced. So Kubernetes was based on a container orchestration system within Google called Bog. And the current version of Kubernetes that we know was built based on Bog, and it was open sourced in 2014. So this year we had the 10th anniversary of Kubernetes. And basically what Kubernetes does is it manages these containers for you. So in the diagram that we saw here, of course, containers does solve a lot of our problems in shipping the software, but how do you ensure that the containers themselves are running? So if you have like very few amount of containers, let's say if you have like 2 containers for your application, you might be able to manage it yourself. But if you're talking about like hundreds or thousands of containers, it becomes increasingly difficult to manage it all on your own manually. So that is where something like Kubernetes comes into the picture. And with Kubernetes, we can manage like hundreds or thousands of containers. You might have heard some numbers in the keynote talks the last 2 days where people are running like millions of CPU cores worth of Kubernetes clusters. So this is a quick, like a very high level overview of what Kubernetes itself looks like. We won't go deep into this in this talk, but I just want to explain some of the different items here. These rectangles that you see, which are labeled node, are different machines in which the code is running. So we have something called the Kubernetes control plane, and we have a set of different worker nodes. So the Kubernetes control plane itself is what is responsible for maintaining and orchestrating these containers. And as we create new containers, Kubernetes would schedule them. It means that it would run them on these worker nodes. And you can have as many nodes as you want in your Kubernetes cluster. You can have different kinds of nodes running different kinds of workloads. So compared to VMs, this is like painting on a canvas versus painting on a binder, to which you can add and remove pages, and you can add and remove different kinds of pages there. So a VM was more fixed. It would have been difficult for you to like quickly change things, but if you had a Kubernetes cluster, and let's say you had a requirement where you wanted to run a specific set of workloads on a GPUs, you can have a Kubernetes cluster have a certain node group which has a certain number of machines which have access to GPUs versus which don't have access to GPUs, and you can you can schedule your software across these different machines. So I have a demo right now. So for those of you are following along, please feel free to interrupt me if you're stuck at any point. I hope you all are able to like follow along and do what I'm going to show you here. So before I start sharing my screen and showing the demo, I wanted to give a quick rundown of what we'll be doing. We will see how we can install Docker and set up a Kubernetes cluster with Kind. So Kind stands for Kubernetes in Docker, and Kind is a software that lets you provision Kubernetes clusters within your machine. So in the diagram we saw earlier, we saw that a Kubernetes cluster can have multiple worker nodes. So in our case, since we only have one, since we are working on a single laptop, what we will do to simulate this is we'll use Kind, and Kind creates, let's say if you want a Kubernetes cluster with 3 nodes, Kind will create 3 different Docker containers, and each of these Docker containers would act as a node in your Kubernetes cluster. And you can like interact with this cluster and like work with it just as how you would work with an actual Kubernetes cluster which has 3 different machines. And we'll see how we can work with the cluster and schedule workloads. And we'll then go back to the code that Emily had shown in the Google Colab. So we'll take that code and we'll see how we can package it so that we are able to run it on a Kubernetes cluster. And then we'll also see how different it is for us to run it on a machine which has only CPUs versus a Kubernetes cluster which has access to GPUs. So yeah, that is the final part of the workshop where we'll see how we can schedule and run these like machine learning workloads on GPUs. So those who are following along, like, is there anyone who does not have Docker installed on their machines? So I'm guessing everybody has Docker installed and running, right? All right. So if you haven't already installed kind, we can take some time to do it right now. The website for kind is kind.sigs.kths.io. If you go there and scroll down to the installation and usage section, you can see how you can install kind depending on your system. So if you would like to follow along, you can follow these instructions. Is there, just so that I know how I can like move ahead with the workshop, like, is there anyone who is trying to do this right now? All right. And have you like completed installing it? Okay, sure. Okay, so I'm assuming that nobody is stuck at this point of the talk, and if I move forward, they won't be left behind. All right. So you would need to have kind, and you would also need to have the binary for kubectl in order to interact with this kind cluster. All right. So if I move forward and leave you behind at any point of time, please feel free to stop me. All right. Are you able to hear me now? Okay. All right. So I'll show what I have right now. I have Docker running on my machine. I'm using Docker desktop, and right now I do not have any containers running on my machine. So what I'll do now is I have kind installed, and with kind I can create Kubernetes clusters with any number of nodes. So what I will do right now is okay, I hope you're able to see my screen. So with kind, I hope you are able to read these as well. Like, please let me know if I need to increase the font size. Okay, cool. All right, so with kind, you can create clusters. You can create Kubernetes clusters in 2 different ways. You can either do kind create cluster, and it would create a Kubernetes cluster with the latest like the image that is present in the machine. And since we did not pass any other configuration here, it would just create a Kubernetes cluster which has a single node. But if you want to like customize your cluster, you can create a like a configuration file with which you can like configure how many nodes or what all are the different properties that you want in your cluster. Like what all feature gates do you want to enable, or if you want to test version skew or things like that. You can simulate like real world behavior as closely as possible with kind, and the kind cluster configuration lets you do that. So now we see that when I ran kind create cluster, it says it created a cluster. I'll open my Docker dashboard again. you can see that there is a Docker container running in my machine now. It's called kind control plane. And what kind does is it creates this cluster and it updates my kubeconfig file. So I have a tool called kubectx with which I use to switch between cluster configs. So you can see that the latest, like the entry that I'm on right now, it's just called kind. And if I do kubectl get nodes, you can see that it says the cluster that I'm currently on has a single node called kind control plane. And if you compare this with the Docker container that is running, it is the same, the name of the container is same as that of the Kubernetes node that we have running. So we have a single node Kubernetes cluster in our machine right now. So this is how you create Kubernetes clusters with kind. You can, okay, I'll quickly go back to the kind documentation here, and you can, let me just search for kind config. If you go to this page in the kind documentation, you can see how, like what all are the different ways with which you can configure your cluster. So you can enable feature gates across all the different components. Like you can, if you define the feature gates at the top level, it will enable these feature gates across all the different components, such as the kube API server, the kubelet, and all of that. You can also have like more granular control, and you can like configure a particular subcomponent of the cluster. So now that we have a cluster, we'll go to the rest of the talk. So I had shared the GitHub repository, and in the README file of that repo, I have commands for everything that I am planning to do here. So I've cloned the GitHub repo locally, and I have two different folders called Flask app Hello World and Flask app GPU, and I will be walking through all the different commands and steps that I've written in the README file here. So first, what we will do is I will show you how you can like package a simple Flask app, how you can create a Docker file, and how you can build the Docker image for the Hello World app, and how you can run it on a Docker, run it with Docker on your machine, and B, how you can run it on a Kubernetes cluster. And after that, we can we'll go into how you can package Emily's code that we saw earlier, and how we can deploy that on a Kubernetes cluster. So first, I'll go into the Hello World code that I have. So this is a very like a simple Flask app which just renders the string hello kubecon, and I have a Docker file here. So this is the entire code for the app, and I have a Docker file here which has all the necessary information to be able to run this app with Docker. So we start with the Python base image, and we copy over all the files that we have. So we copy over the app.py file, the requirements.txt. Those two are the only important files in this context. And we do pip install from requirements.txt file so that it installs the Flask dependency that we have. And we expose port 5000 of the Docker container. Why we expose port 5000 is because inside app.py we have defined the port at which the app is running to be 5000. So we do that, and we start the Python app. So with that, we'll be able to run. So once we build this container image and once we start running this container, we'll be able to access the app. So I'll quickly show how we can do that. So I'm inside the Flask app Hello World folder here. Now I'll come over here and I'll copy over the commands. So for building the Docker images, I'll use the Docker build command, and I'll tag this Docker image with the name hello kubecon latest. So if you run this right now, it will pick up the Docker file that we have, and it will create the Docker image for us. So once this gets completed, you will have a Docker image on your machine called hello kubecon latest, and you can, all right, so now that it has been completed, you can, you can start a Docker container in your machine. So I'll show you what all containers are running on my machine right now. We only have a kind cluster that we saw earlier. And once I run Docker run and I pass this particular container image, it will start a container with the image that we just created. So I'll explain what I'm doing with the port here. We had exposed port 5000 of the container, and the app itself is also like being served on port 5000. But I don't want, like if I run the container, the port 5000 that we should access is inside the container. So we need to map that to a particular port in our machine so that we can access it, so that we can access what is going on inside the container from our local host. So I'm passing, so here when I do -p, I'll first pass like what port it is that you want to access the container in your machine and what port it should forward it to inside the container. So that's what this line does. And if I start this, you can see that like this is what you see when you start Flask. And if I go to localhost 3000 right now, you can see that it says hello kubecon, and this is the output of the Flask app. So you must have noticed that I did not install Python in my machine. At least in the context of the talk, I did not do anything. I already have Python in my machine, but that is not relevant. Even if you did not have Python, you could have run this Python app using Docker. So that is the whole reasoning of Docker that we had explained earlier. So now that we have this running, I have an image called hello kubecon latest in my machine. So this is still running in my laptop, and if I exit out of this, you can see that this is no longer like accessible. But now if you want to, so now that you have an application that you containerized and you're able to run the container, you want to be able to make sure that the container itself is like running healthily, and if something happens to it, such as if it gets killed, that it should come back up and things like that. So you want to be able to orchestrate the containers and container and make sure that it is running properly. So for that, we can deploy our container, deploy our app as a container inside our Kubernetes cluster, and that is what we are going to do now. So inside the same Flask app hello world folder here, we have another file called pod.yaml. So what happens here is I'm defining a pod. A pod is a concept, an abstraction inside Kubernetes. I'll explain what that is in a minute. But we create a pod in Kubernetes which has a container image specified. So the image that I've given here is different because the image that we just created right now with Docker build, that exists in my machine. But if I want to be able to use it inside my Kubernetes cluster, I need to load the image first inside the cluster. So you can do that. You can load the image using kind. But what I've done here is I have tagged the image with a different name, which is what you see here. And this is my public Docker Hub account. So I've pushed the image to my Docker Hub account so that I can access it from anywhere. So I have a pod manifest which has some metadata like the name, labels, and all, and which namespace inside the Kubernetes cluster it has to run. And inside spec, you can see I have defined a containers section here. And a pod is basically a abstraction around containers in Kubernetes. A pod can have multiple containers inside it, but the main reason we want to have, like we want to group multiple containers together is because they can share the same file system and the same network namespace. So usually a pod only has a single container, but unless there is a requirement where you want to have multiple containers which has access to the same file system, we don't usually do that. So it might be confusing when you're learning Kubernetes for the first time what the difference between pod and container is and why we need a pod. When while you're using Docker, we don't have this abstraction on top of containers. You are familiar with running containers by themselves. But the reason that we have something like a pod in Kubernetes is because there might be requirements where you would want to run multiple containers which has access to the same resources. So that's why we have something called pod, and this is how you define a pod. And if you want to have one more container here, I'll quickly show how that works. You can add another container in this list. So when this manifest is submitted to the Kubernetes API, the format of this YAML file that we see here, that the Kubernetes API as a schema, and inside the schema, this containers field is an array, so it can have multiple containers. That's how it works. So I've given a name and I've passed my image, and here also I've specified the port 5000. So this is similar to how we expose port 5000 in the Docker file. So now that I have a Kubernetes cluster running, if I do kubectl get nodes, I can see that there is a single node running. If I do kubectl get ports, there are no ports running in the cluster yet. But if I do kubectl apply and I pass this pod.yaml file, it would create a new pod with the name that I specified in the YAML file, and it would try to pull this container image. So let's see if that works. So now you can see that there is a pod called hello kubecon and it is running. So what we can do now is I can look at the logs of this pod. So I can do kubectl log pod hello kubecon, post kubectl logs, and you can see that the logs of the pod has the same information that we saw when we ran the Flask app as a Docker container in our system native. So now that we have the pod running, we'll see how we can access it. So this is all, like we just went through all this information here. So the pod is contained inside the Kubernetes cluster, and the only way we were able to see the logs is using kubectl. So kubectl talks to the Kubernetes API and gets all this information. So without having the necessary authorization to be able to use the API, you won't be able to access the pod unless it is exposed outside the cluster. So there are different ways, there are different levels at which you can expose containers and pods running inside the cluster out to outside the cluster. And this is done with a concept called services in Kubernetes. And there are different types of services which can expose workloads on different levels outside the cluster. So now what we'll do is we'll create a service. We'll create something called as a cluster IP service. So what this does is it exposes the pod that we just created within the cluster. So if we run this command, it would expose the hello kubecon pod, and it would expose the port 5000 of this particular pod outside within the cluster. So if you run this command, you can see it says service hello kubecon expose. And if you do kubectl get services, you can see that there is a service called hello kubecon right now. And it has a cluster IP, which is the IP of the container inside the Kubernetes cluster. And port 5000 is exposed. So now that we have a service, you can like have a load balancer which points to the service. But in order to test this locally, like if you're running this on an actual Kubernetes cluster, you can provision a load balancer which would point to this IP, and you can link that with the DNS, and you will be able to access things which are running inside the cluster from anywhere in the internet. But since we are not having a load balancer right now, we'll do something called port forwarding. So what this does is it takes a port in our local machine, and it forwards the traffic that forwards all the requests that that gets sent to this particular port to inside the cluster, and that is done via the Kubernetes API. So if I run this command kubectl port forward, I specify the service, and I specify again similar to the Docker run command. I say that I want port 3000 of my local machine to point to port 5000 of the cluster IP service, which is named hello kubecon. So if I run this command, it says forwarding. So you need to keep this open. This is like a tunnel. And you would have noticed that earlier when we went to port like workloads 3000, we were not able to access the app once we stopped the container. But now that we have the pod running, and now that we do the pod forwarding, we are able to see the app back up again. So what is happening here is that when you type in localhost 3000 in the browser, uh, we have a tunnel running in our system which accepts requests which are sent to localhost 3000. And since we have the port forwarding like running, it will take all the traffic that is sent to port 3000 and it would send it to the send it inside the cluster, and it would point it to the particular cluster IP service that we have specified here. It would point it to the this particular cluster IP and this particular port of that cluster IP service. So the app that we are seeing here right now is being served from inside the Kubernetes cluster. All right, so that is how you would package. So now we saw the end-to-end process of how you would take a regular like application, like a regular like a web server in this case, and how you would package it as a Docker, like an OCI, like a container image, and how you would run that container image on a Kubernetes cluster. So you can follow a similar process with the code that Emily had shown. So I have a different I have another folder inside the same repo. It's called Flask app GPU. I will walk through the code and I'll try to explain what I'm doing here. So this is the app.py file. What we are doing here is we are doing all the same setup that Emily had done in her code in the Google Colab notebook. So we clone Emily's branch of Emily's fork of the scikit-learn repository, and we compile compile scikit-learn from source so that we have array API. So if you remember earlier in the talk, it was mentioned that array API, the array API support that Emily had shared has not been merged to the main branch in scikit-learn yet because work is still happening. So we need to use a dev branch and compile scikit-learn from source in order to be able to use the feature. So whatever setup, so in Google Colab, if you add a exclamation mark at the beginning of the code block, it would run that particular command in the system. So this is basically like running a bash command. And like if you have code which does not have that like bang symbol or the percentage symbol, then it would like execute that Python code. So we do all of this setup. So you can see that we have a bunch of commands which have this bang symbol at the beginning. We run all of that. So that is actually run inside the Docker file. So this is the initial setup that we want to do in order to be able to run the app. But inside the app.py file itself, we can see that we have all the code that is there in the final code block here. So we have all the imports. We have all the imports of all the different libraries that we are using, and we set up everything as Emily had described in her portion of the talk earlier. And we have at the end we run this fitting of the ML model against CPU and GPU. So we do the same thing in the Flask app, but what is different here is that I have a little like HTML page which has two buttons called use GPU and use CPU. So what I was trying to do here was we'll have two different buttons, and whenever you click on each button, it would run that respective block of code. So if you click on run GPU, then it would run this piece of code which would do the model fitting against the GPU using the GPU, and you would be able to see the time difference. But in order to be able to run this, you would have noticed that in the code that Emily had shared earlier, when we create the random data using Torch, using PyTorch library, we are specifying the device as CUDA. So this means that this needs to be run on the GPU. So if you try to run this code on a machine that does not have access to GPUs, it would throw an error saying that NVIDIA drivers are not found. So I am not able, like I won't be able to show you the code running on my machine. So what we can do is we need to set up a Kubernetes cluster which has access to GPUs. So I tried doing that, but I had some difficulty with setting up the NVIDIA drivers. So I can't show you the demo of running the code on a Kubernetes cluster right now, but I have all the setup that is required to be able to do that. And if you are running this on a machine which has access to GPUs, you would be able to run it just like how we ran the Docker containers right now and get that output. So the code itself is identical here, and the output also that you would see is identical. You would be able to see this output and see the time difference between running the same code against CPU and the GPU. Right. I'll talk a bit more about how, like this is just the code of the application itself. I'll talk a bit more about how you would go about creating the container image and how you would deploy this on a Kubernetes cluster. So in the Docker file that we have here for the Flask app that uses GPU and runs this scikit-learn code, what we do is all the setup that we have done in the initial part of the notebook, we'll do all of that in the Docker image. So at the end of the Docker image, when we start the application, when we start the Python server, it would have all these dependencies already installed. So this Docker file is actually the same as the one that we saw for the earlier Hello World app. So here what we do is we copy over all the files and we expose the port and install all the dependencies. We do all the same things here, but before we do that, we also clone Emily's fork of scikit-learn. We compile scikit-learn from the source and we use that to, like we can see here, this block, what it does is it clones the repo and we cd inside the scikit-learn folder and then we install a bunch of dependencies. After that, we again run this command to compile scikit-learn from source so that we have access to the array APIs. And we make sure that scikit-learn is installed properly. So if at this point, if you don't have, actually even if you don't have a GPU, it would still work. But when it comes to the code, where we mention the device as CUDA, then at that line of code, it would break if you are running this on a CPU. So what I have done here is I have changed the device to say CPU instead of CUDA. So in all the places where we use PyTorch to generate the random data, I've mentioned the device as CPU instead of CUDA. So if you make this change in the code, you will be able to run this on a CPU and not, even if you don't have access to a GPU, or even if you don't have access to a Kubernetes cluster that has access to a GPU, you would still be able to run this code. But the only difference would be that it would take longer, and the time difference that you saw at the end of the notebook, you won't be able to, if you're running both of these on a CPU, you would be finding similar times for both these blocks of code. So that is the application code that we have. And again, we went through the Docker file which does all the setup. And similarly here again, we have a different pod.yaml file. So what we do here is we build this new Docker file that we have, which does all the initial setup, and we use that image instead to create our pod. And if that pod is running on a machine that has access to a GPU, then all the code that we saw in this file, which uses CUDA, would be run. And since we compiled scikit-learn from the source in our Docker file, it would use the array API to do this ML model fitting. And yeah, we can do that, but the thing is that the array API is still being developed, so it is not available in the scikit-learn main branch. So once it gets merged, so at the end of the video, Emily had shown a meta issue which has all these issues which are related to the array API. So once those are completed and once everything is merged to the master branch or the main branch of scikit-learn, and once they release a new version, then you will be able to import scikit-learn directly and use these features. But since this is a feature that is still being worked upon, you would need to do this hack of having to compile from source. Yes. Uh, I am not entirely sure about that, but it does make sense that we should be able to do that. So if like if you are able to do that with any GitHub repository, like if it lets you do that, then that should be possible. Right. We are not changing local code. Okay. Right. Yeah. Then that makes sense. Then we can replace in the Docker file. We can probably replace all these lines with pip install, which is pointing to her fork of the repo. Yeah, I'll try that out today. Uh, yeah, I'll go back to the repo that I had. Yeah, so unfortunately, since I don't have access to a cluster which has a GPU, I tried my best, but I was not able to set it up properly. Like I'll walk through the different steps that we need to do. So we would essentially follow all the same steps. We would build the Docker image, and inside this Docker file, we have the logic for compiling, like using Emily's fork of scikit-learn. And once we start the container, the Flask app would have the logic for generating the data using the array API, and it would be run against the GPU. So if your machine has access to a GPU, then you would be able to run that code in your machine itself. And if you have a Kubernetes cluster which has access to GPUs, then when I say a Kubernetes cluster which has access to GPUs, what I really mean is that the worker nodes of the Kubernetes cluster would have GPUs installed on them. So if you have such a cluster, you would be able to apply this pod.yaml file against the cluster and like run all the code that you ran in the Google Colab notebook on a Kubernetes cluster. So you can do the same to like export the same steps to expose the code outside the cluster and access it how you did the Hello World app earlier. Yeah, with that, we are at the end of the demo. So I do have some additional resources to share. Uh, so the first one is a document in the Kubernetes documentation about scheduling to GPUs. So this has more information if you would like to, if you're interested in this area, like how you can schedule workloads on GPUs. I just skimmed over the bare basics. There is also something called dynamic resource allocation, which is a more advanced feature that is still being worked upon in Kubernetes, and it is outside the scope of this talk. But basically, what dynamic resource allocation lets you do is it lets you uh, like have more control over GPUs. You might have heard Arjun mention dynamic resource allocation in his keynote talk earlier today. There is also another project called JobSet, which is also a way, basically JobSet lets you run like multiple jobs on a Kubernetes cluster, and it is meant to be used for distributed machine learning training workloads, which might also be interesting for you if you're trying to do ML stuff on your Kubernetes clusters. Yep, as Emily had mentioned earlier, I'm showing the slide again. You can take a look at these links which point to the scikit-learn docs. You can also contact us if you have any questions. Yeah. No, there is no difference. The only difference that I wanted to show here was how we use the libraries and all the setup that we had done for like, whatever we had done inside Google Colab, like how we would translate that to a Docker file. So right. You have something called as node selectors. So actually there are multiple ways in which you can do this. There is something called node selector. So depending on your different workloads or different pods or deployments, if you want one particular pod to run on a machine that has a GPU, you can mark that pod, like you can set a node selector which would specify that this pod would only run in these sets of machines or this particular machine. All right. So to answer your first question, like it doesn't really depend on what the kind of application, like what kind of software you're running. Like as long as you are scheduling something on a Kubernetes cluster, you have the control over where each like deployment should be scheduled to. So you can, so let's say you have two different apps. One of them uses scikit-learn to use like the GPU. You can mark the pod so that it gets scheduled only on machines which has access to GPUs. So I think how so I am not entirely sure if I understand your question correctly, but what I yep. But I believe that depends on the kind of code that you're running, because here itself you can like all this code is being run against this particular T4 GPU, right? So it depends on which function that you use. Like the function that you use like decides where the code is being run. Yes. That would, I believe that would be run against the CPU, because here when you're doing the fit using NumPy arrays, that is actually being run against the CPU, right? I guess you could put it that way. So it depends, like if your code requires GPU to be able to run, then you can only schedule it on a GPU. But if your code can run on a CPU, like you can run it on machines which has or has not have, like which does or doesn't have access to a GPU, but that won't make a difference. That is what I understand. Right. I've not actually done this. I've done scaling, but I've not done it using machine learning code. But there are ways with which you can automatically scale Kubernetes pods based on the resource utilization. I believe vertical pod auto scaling lets you do that. So does anyone have any questions? All right. If not, thanks a lot for sticking till the end. I really appreciate it. I hope you had a great 2 days at the conference, and feel free to reach out to us if you need any help, or if you are interested in like getting started with contributing to scikit-learn or Kubernetes. Thanks, folks.